Hello everyone, my name is Mohammad Sohaib Amjad and welcome to my presentation session. In today's talk, I will be presenting my paper titled as Inband Full-Duplex Relaying for RADCOM-based cooperative driving, which is co-authored by Max Schuttler, Sigrid Demche, and Professor Falco Dressler. It's a well-known fact that cooperative driving is the backbone of today's intelligent transportation system. In cooperative driving, the driving vehicle is designed to gather and share information from its surrounding vehicles and infrastructure, and accordingly adapt itself to environmental and traffic conditions. But in order to gather and share information, the driving vehicle requires a communication link. And the conventional communication systems are based on sub-6 GHz spectrum, which is intensely utilized. And in dense traffic situations, such as here shown in the figure, where every vehicle may try to access the channel, could lead to channel congestion, which cause excess delays. This is typically not desired in safety and time critical applications of cooperative driving. So, what we are proposing here in this work is to use RADCOM for cooperative driving. RADCOM is short form of radar based communication, and it's actually the dual purposing of radar detection and ranging system with millimeter wave communications. The, the latest vehicles are already equipped with radar sensors for detection and ranging purposes, and they operate in the 77 gigahertz millimeter wave band. What we are proposing here is to use millimeter wave communication with this detection and ranging system. Why are we opting for millimeter wave? It's because they have huge available bandwidths, which can essentially complement the existing sub 6 gigahertz spectrum and offload some of the traffic from these channels. Also, since these radar systems are already there in the latest vehicles, what we have to do is additionally just integrate the communication parts, which makes the system less expensive. Here we are exploring the potential of RADCOM for platooning use case. Vehicle platoon is a group of connected vehicles following each other at short inter-vehicle distances. Within the platoon, there is a leading vehicle that broadcasts the message to all the following vehicles at regular intervals. These messages contain the information of maneuvering and other road traffic conditions. It is required from the leading vehicle to maintain a reliable communication link with all the following vehicles, and especially the last one, which is furthest away. And if the link quality is weak between first and last vehicle, then the leading vehicle essentially needs to increase its transmit power. And higher transmit power means large interference domain with the ambient vehicle. Also, if the platoon size is increased, this means that more transmit power is required to maintain a reliable link, which means more interference domain, which is again not desired in already congested spectrum. Now we know the fact that millimeter waves experiences high propagation losses because of smaller wavelengths. As a result, they can only communicate over shorter distances. Therefore, the traditional approach of broadcasting the message in platooning is not feasible for RADCOM. This made us look into the approach of message relaying. In message relaying, the leading vehicle only needs to send the message to its immediately following vehicle. And this immediately following vehicle only needs to relay the information to the preceding vehicle. In this way, the whole platoon receives the message eventually. This essentially reduces the interference domain as now the leading vehicle only need enough transmit power to send the information to the following vehicle. Additionally, higher order modulations can now be adopted by the leading vehicle as it only needs to communicate over shorter distances, which increases the information rate at the end. However, this message relaying comes at the price of a linearly increasing end-to-end delay, especially at the last vehicle. This is again not desired in safety and time-critical vehicular applications like platooning. We therefore propose a full duplex relaying in RADCOM. A full duplex relay has the capacity to simultaneously receive and forward the information at the same time and frequency. And it essentially carries all the benefits of a typical half duplex relay, such as small interference domain and the capacity to use higher order modulations. At the same time, it only adds marginal incremental end-to-end delay. And this incremental delay is due to the fact that additional processing is now required at each relaying node to suppress the loop self-interference. For optimal performance of a full duplex relay, this LSI needs to be suppressed. And to do so, we have to regenerate an approximate LSI signal. This regeneration is a two-step process. In the first step, we approximate the loop self-interference channel. Once we have the loop self-interference channel, we simply filter out the known signal with the obtained channel coefficients to regenerate an approximate signal. This approximated self-interference is then subtracted from the actually received LSI, and a successful suppression of LSI basically ensures optimal full duplex relaying. For the implementation of the proposed idea of full duplex relaying in RADCOM platooning, we have created a 5 vehicle scenario in GNURadio framework. For the baseband TXRX implementation, we have used IEEE 822.11p compliant in standard implementation. And also, we have implemented both amplify and forward and decode and forward relaying schemes. And we have also implemented multipath LSI suppression algorithm. It is worth mentioning here that since the millimeter wave have high propagation losses, therefore they offer a very high passive isolation already. So there is no leakage of the direct component. So therefore, we only need to model the multipath loop self-interference, which we have done in the digital domain. Now, for the millimeter wave channel, we have used a MATLAB-based NYU simulator, which is also called New York simulator, to generate channel coefficients. We have then imported these channel coefficients into the GNURadio framework to emulate a millimeter wave channel within the framework. So the channel has the following properties. It's a 77 gigahertz millimeter wave channel with 800 megahertz bandwidth. Also, we have simulated two channels. First channel is between the vehicles, and it's a line of sight length with a separation distance between vehicle of 5 meters. This 5 meter is the standard defined inter-vehicle distance in typical platoon use cases. The second channel that we have simulated is the loop self-interference channel, and it is considered as a non-line of sight link with 4 meter distance between the front and rear antennas. The rest of the implementation details can be found in our paper. This first performance results show the required transmit power from the leading vehicle to maintain 100% packet delivery ratio at every following vehicle, that is from vehicle 2 to vehicle 5. And the plot here also shows the performance for the lowest and the highest order modulation encoding scheme that is defined in the 802.11p standard. So now let's just focus on 64 QAM 34 performance. And if we further compare the performance of amplify and forward and decode and forward relaying, we see that the transmit power requirement increases with vehicle number in the case of AF relaying. This is essentially because the fact that the amplify and forward relay also amplifies the noise factor at every vehicle. As a result, more transmit power is required from the source or the leading vehicle to overcome the additive or the amplified noise factor with the preceding vehicles. Whereas in the case of DF relaying, the relay node decodes and reencodes every packet. And as a result, the noise factor is eliminated entirely at every relaying node. That's why we have very consistent transmit power requirement with DF relaying. Now, if you further compare the performance of half duplex relaying with full duplex relaying, we can see that the full duplex relaying is performing roughly 1 dB worse as compared to half duplex relaying. This is essentially because of the fact that we have residual loopback self-interference, which raises the noise floor from for the relaying for the relaying signal, and as a result, more transmit power is required in the case of full duplex relaying. Now, the second result demonstrate the normalized physical layer latency at vehicle 5. Overall, the plot shows the total end-to-end delay that we have measured at vehicle 5. So before going into the detail, let's just focus on decode and forward full duplex relaying plot. And we can see that as soon as the transmit power is increased from minus 23 dBm, the relay node starts to receive packet, and the overall latency drops down with increasing transmit power. This is essentially because with more transmit power, a higher order modulation encoding scheme can be adopted, which reduces the size of the packet. And as a result, we observe less end-to-end delays. If we now compare the performance of amplify and forward with decode and forward relaying, we can see that there is a huge performance difference. This is essentially because of the fact that we need more transmit power from the leading vehicle just for the amplified forward relay to start receiving the packet. And that's why we have worse performance with AF relays. Also, if we compare the performance of half duplex relaying with full duplex relay, we can see that there is roughly 4 times more end-to-end delay that we observed with half duplex relaying. This is essentially because of the fact that a half duplex relay has to wait before forwarding. And this waiting time basically increased the end-to-end delay as opposed to full duplex relaying. To sum up, in this talk, we presented the idea of RADCOM for cooperative driving and we evaluated the proposed technique in vehicle platoon use case. Because of the short communication ranges in millimeter wave, the traditional approach of direct dissemination of messages is not a fully feasible option in RADCOM-based platooning because higher transmit powers are required for reliable communication of the messages, which means large interference domains. We therefore explored the idea of message relaying, and we first looked into half-duplex relays, and where we observed linear incremental end-to-end delays, which only grows with platoon length. And this is essentially not required in safety-critical applications such as platooning. We then proposed the idea of full duplex relaying in RADCOM platooning, where for optimal performance, LSI suppression of the noise floor is a definite requirement. We evaluated RADCOM full duplex relaying for a 5 vehicle platoon scenario where we found out that DF relaying outperformed AF relaying in every aspect. A typical DF relay requires low transmit power, which means it's energy efficient. Additionally, DF showed less end-to-end delays, which means small channel busy time. Well, this concludes my talk. Thank you very much for watching, and bye bye.